What if one aircraft could replace an entire fleet, fighters, strike jets, and even vertical landing attack planes, while staying almost invisible to radar? That aircraft is the F-35B, one of the most advanced combat jets ever built. It merges the roles of the F-16, the Harrier, and even stealth bombers like the B-2 into a single machine. Agile in air-to-air combat, lethal in ground attack, and built around cutting-edge stealth technology perfected through planes like the F-22 Raptor and F-117 Nighthawk. The jet sensor network is just as important as its weapons. The F-35's onboard systems collect and fuse battlefield data, instantly sharing it with nearby friendly forces without exposing the aircraft's position. All of this information is projected directly onto the pilot's helmet visor, delivering a real-time, 360-degree picture of the battlespace. In combat, groups of F-35s fight like a single connected system, almost a flying hive mind. And then there's its most jaw-dropping trick. With the press of a button, the F-35B can shift from conventional flight into full vertical landing mode. A hidden lift fan and redirected engine thrust allow the jet to land like a helicopter, even on the short decks of U.S. Marine Corps amphibious assault ships. Packing this level of flexibility into one airframe is an engineering nightmare, requiring thousands of trade-offs between stealth, aerodynamics, weight, and performance. Stealth itself is widely misunderstood. It doesn't make aircraft invisible. The real goal is to delay detection, confusing enemy radar long enough to slip through defensive gaps or strike first. In fighter combat, stealth delivers the ultimate edge. See the enemy before the enemy ever sees you. Radar reflection is hardest to eliminate when flat surfaces act like mirrors, sending signals directly back to enemy receivers. Even worse are corner reflectors, where two surfaces meet at right angles, bouncing radar waves straight home. Conventional tailplanes are ideal reflectors, which is why stealth aircraft must dramatically rethink stabilizer design. Some aircraft, like the B-2 bomber, remove tails completely. Others, such as the F-117, use a VTOL, combining rudder and elevator functions into angled control surfaces. By deflecting those surfaces in opposite directions, yaw is controlled. Deflecting both together produces pitch control. But fighter jets demand far more authority than a single multi-role surface can provide. That's why the F-35 and F-22 also use large, angled elevators, carefully offset to avoid creating radar hunting corners while still delivering the aggressive maneuverability modern air combat requires. Each design choice reflects a balance between stealth and control, and comparing early stealth jets like the F-117 with modern fighters shows how those compromises have evolved. Engine design reveals another stealth challenge. Aircraft like the B-2 route air intakes along the top of the aircraft, shielding them from ground-based radar and reducing infrared signatures. But that setup restricts airflow during extreme maneuvers, a fatal weakness in dogfighting. Placing intakes underneath provides better airflow, but dramatically increases radar visibility. The F-35 solves this with side-mounted twin intakes, combining optimal airflow with reduced radar exposure. Look closely and you'll notice a strange bump near the inlet. This is a diverterless supersonic inlet, DSI, one of the jet's most elegant engineering solutions. As air flows along the fuselage, a slow, turbulent boundary layer forms. If that air enters the engine, efficiency drops and turbine blades experience damaging stress cycles. Earlier aircraft used physical gaps to divert this boundary air, but the gaps increased drag and radar signature. The DSI bump fixes this by compressing incoming airflow to push the boundary layer away from the intake naturally, while also scattering radar waves. The result is impressive: lower weight, less maintenance, reduced cost, and better stealth. Even the jet's smallest features serve the stealth mission. Long, sharp edges scatter radar, so designers reduce their effectiveness by breaking them into serrated patterns. On bombers like the B-2, this is obvious along the trailing edges. On the F-35, it's subtler, filled with serrated doors, access panels, and hatch seams across the fuselage. These include the cockpit ladder door, landing gear bays, internal weapons compartments that hide missile reflections, and small flare dispenser hatches. Flares remain vital against heat-seeking missiles, even as radar-guided threats dominate modern battlefields, proof that survival still depends on layered defense systems working together. Every groove, curve, and panel on the F-35B tells a story of compromise, ingenuity, and battlefield necessity. It isn't just a fighter jet, it's a flying fusion of stealth science, naval versatility, and digital warfare, built to dominate skies where visibility means survival. From the outside, the F-35 looks like any other fighter jet, but hidden inside its skin is a silent battle system that can confuse missiles, bend radar waves, and even trick weapons into chasing ghosts. A specialized decoy system sits behind a discrete access panel. When activated, the door opens and releases a small transmitter on a fiber optic tether, safely trailing behind the aircraft. This device becomes the F-35's last line of defense, and it works in 3 powerful stages. First, it actively jams incoming missiles while they are attempting to lock on. The jet's onboard computer calculates precise interference signals and sends them through the tow line to the emitter, drowning out the missile's guidance system. If a radar lock still forms, the system shifts tactics, attempting to break that lock by disrupting the tracking algorithms guiding the missile toward the aircraft. And if the threat continues closing in, the emitter creates a false radar signature that mimics the F-35 itself, luring the missile away as a decoy and sacrificing the drone instead of the jet. Those jagged, serrated panels you see across the airframe hide critical components, but they also do more than protect hardware. Look closely, and you'll notice the edges are a different color than the rest of the aircraft. That's because they're coated with special radar scattering tape. Radar waves behave much like ocean waves. When they hit a sudden edge or change in material, they scatter. The tape exploits this effect. It uses a graded conductivity layer that slowly reduces the strength of surface-traveling radar waves, scattering them over distance before they ever reach sharp edges. Without this treatment, those waves could reflect back in a single strong burst, instantly revealing the jet's location. Beneath the surface, the F-35 is built from advanced radar-absorbing composites. In 2010, Lockheed Martin patented a carbon nanotube-infused material capable of absorbing radar frequencies from 0.1 MHz all the way up to 60 GHz, an enormous range that includes the tracking bands used by advanced Russian surface-to-air systems, including the S-400. Even the aircraft's shape reflects this stealth science. Although curved surfaces usually scatter radar waves, cylinders can carry surface waves around their circumference, sending them straight back to the radar source. That's likely why the F-35's nose cone includes a sharp ridge to break up what would otherwise be a smooth circular profile. In contrast, the F-16's nose remains nearly perfectly round. Curiously, the F-35's largest hatch is not serrated, and there's a reason for that. This hatch protects the massive lift fan used during short takeoffs and vertical landings. The fan acts like a vertical helicopter rotor, generating 85 kilonewtons of lift and creating an intense low-pressure zone above the jet that pulls air inward at nearly 90 degrees. To keep airflow smooth and efficient, the inlet hood must allow uninterrupted airflow, and serrated edges would cause turbulence, reducing lift performance. Early prototypes of the aircraft used 2 side-opening doors, but the final design switched to a rear-hinged hatch. This improved airflow into the engine and significantly boosted pressure recovery, especially during short takeoffs where vertical lift blends with forward thrust. When the transition to vertical flight begins, a heavy-duty clutch engages the extended drive shaft from the main engine. Nearly 29,000 horsepower is transferred into the lift fan gearbox, spinning the counter-rotating blades beneath the cockpit. At the same time, the rear exhaust nozzle transforms. Called the 3-bearing swivel nozzle, it consists of 3 sealed segments cut at precise angles. Together, they rotate smoothly, redirecting engine thrust downward. The central section alone moves the nozzle to 45 degrees, ideal for short takeoffs that balance forward push with vertical lift. This allows the F-35 to launch from compact assault ships like the USS Macon Island, just 258 meters long, or even shorter decks aided by ski jump ramps. For vertical landings, the nozzle completes its rotation to a full 90-degree downward angle. Additional nozzle segments keep thrust centered so the aircraft remains stable during this delicate transition. But thrust control doesn't stop there. Compressed bleed air from the main engine feeds 2 roll nozzles built into the wings, providing side stabilization far from the jet's centerline. Beneath the lift fan, adjustable guide vanes fine-tune airflow, altering thrust direction from 5 degrees forward to 42 degrees backward to maintain balance throughout the hover. With all these computer-controlled systems working together, the F-35 is dramatically more stable than older VTOL aircraft like the Harrier, allowing it to hover on 2 invisible columns of air with precision control. Powering all of this is the Pratt & Whitney F-135, derived from the F-22's F-119 engine, but pushed to even greater extremes. Although the Raptor uses two engines producing 156 kilonewtons each, the F-35 relies on a single engine generating 191 kilonewtons of thrust. Its massive fan and high bypass ratio provide exceptional cruise efficiency and a huge mass airflow, essential for vertical lift. But this design has a trade-off. Bypass air never enters the combustion chamber, meaning it doesn't gain full acceleration, lowering exhaust velocity and ultimately limiting top speed. The F-35 maxes out at Mach 1.6, while the F-22 can reach Mach 2.2. The F-35 was built for endurance and mission flexibility, not outright speed. Yet the vertical lift hardware itself creates challenges. The lift fan module alone weighs 1.2 tons, dead weight during normal flight that also steals space from internal fuel storage. To counter this, engineers pushed for extreme weight reduction. Inside the fan are two counter-rotating titanium blisks, single-piece blades integrated directly into their discs instead of being bolted together. This eliminates weak points, boosts efficiency, and reduces mass. Even more impressively, the first-stage fan blades are hollow, shaving off critical weight without compromising strength. It's a manufacturing feat as ambitious as the aircraft itself, and yet another reason the F-35 stands as one of the most technologically complex flying machines ever built. The real magic of the F-35B isn't what you see on the outside, it's the digital battlefield happening inside the pilot's helmet. Unlike older fighters like the F-16, where the heads-up display is fixed to the cockpit panel, the F-35 puts all critical flight and combat data directly into the pilot's helmet visor. No more looking down at instruments during a fight. Wherever the pilot looks, the information follows. In modern air combat, situational awareness is everything, and this helmet delivers it in a way no previous aircraft could. It even provides night vision and what pilots call X-ray vision, allowing them to see straight through the aircraft. Sensors placed all around the jet feed data into a central computer. That information is fused into a single, real-time picture and projected directly onto the helmet visor. Beneath the fuselage, inside a transparent angular housing, sits one of the plane's key sensor systems. These aren't ordinary windows. They're made from sapphire, a rare and costly gemstone chosen for its extreme durability and ability to transmit a wide range of electromagnetic wavelengths, from ultraviolet to infrared. But the heart of the F-35's electronics is hidden in its nose, the radar. This isn't a traditional mechanical radar dish. It's an advanced phased array radar, a flat surface packed with thousands of tiny antennas. Each metal plate you see inside the array contains multiple slotted elements. In total, around 1,600 individual antennas work together as one system. Instead of physically rotating to aim, the array steers its radar beam electronically using wave interference. When signals from two antennas sync perfectly, their waves combine to amplify the signal, a process known as constructive interference. When they're out of sync, the waves cancel each other out completely, destructive interference. It's the same principle used in noise-canceling headphones, which create sound waves to erase background noise. The F-35 uses this technique to shape and steer radar beams instantly without moving parts, allowing precision control while minimizing the risk of broadcasting its position to enemies. Older phased array systems were passive, powered by a single transmitter, meaning they could only track one direction at a time. Lose that one beam, and the target slipped away. The F-35's radar is active phased array, AESA. Every single antenna within it has its own individual transmitter and receiver. This lets the jet track multiple targets simultaneously, aircraft, ships, or surface threats, all at once, with zero mechanical motion. The aircraft's nose cone, known as the radome, must be transparent to radar waves. It's made from specially designed composite materials for this purpose. On older jets, this transparency created strong radar reflections, especially with mechanical radar dishes that had to point directly at targets. With the F-35's electronically steered array, the antennas rarely need to point forward. They're angled upward, allowing unwanted radar energy to bounce toward space, helping preserve the aircraft's stealth profile. But the radar doesn't only find enemies, it handles communication too, and that's where the F-35 becomes truly deadly. Modern combat isn't won by lone fighters, it's won by networks. The F-35 F-35 constantly shares information with other aircraft and ground forces, creating a live, unified battlefield picture. To make this possible, vast amounts of data must be transferred at incredible speed. The challenge is communication itself advertises your presence. Stealth aircraft must transmit securely and discreetly. The F-35 solves this through its radar-based communication system and a specialized encrypted data link called MADL, built on lessons learned from the F-22. MADL allows F-35s to exchange massive data streams rapidly while keeping the signals difficult to detect or intercept. All that shared information, from friendly fighters, ground forces, drones, and onboard sensors, is filtered, prioritized, and sent straight back to the pilot's helmet display. The result: unmatched situational awareness. The pilot doesn't need radio calls to know where enemies or allies are. The aircraft itself communicates and feeds the battlefield picture directly into the helmet. If an enemy plane is flying beneath the jet, the pilot can literally look down through the cockpit floor and see the exact location of the threat in real time. That seamless fusion of sensors, radar, networking, and display technology is what truly sets the F-35B apart. This isn't just a fighter jet. It's a flying combat command center, and that's the real power of the F-35B.